All right, AP Stat students, this is going to be one of the harder chapters for now. Everyone always says that this chapter was really hard at the time, but then we use this stuff the entire school year. So you're going to get it down. So the better you get it down now, the better you're going to be for the whole rest of the school year. So make sure you do a good job on this chapter. I'm just going to hop into it. There's a lot of different topics. None of them are that hard. There's just a lot. So first of all, percentiles. You already know percentiles. You heard about if you're in the 70th percentile, what that means. So the nth percentile of a distribution is the value with p% of the observations less than that. So if you're in the 70th percentile, then there's 70% less than you. So here's a stem plot that shows the number of wins for each of the 30 Major League Baseball teams in 2009. Okay, so this is stem plot, and then there's our little legend. So 5-9 means they had 59 wins. So we want to find the percentiles for the following teams. The Colorado Rockies, who won 92 games. So 92 is right here. We want to know how many are less than that. Well, there's 30 teams. So if we just count 1, 2, 3, 4, 5, 6, that means that the other 24 teams are less than that. So 24 out of 30. So we make that into a decimal, 0.8, which means that this is the 80th percentile. Okay. For both teams who won the 65 games, this is just more practice. So 65 games, the Royals and the Indians. So it's both. Remember, it's the number that are less than it. So 1, 2, 3, 4, 5, 6, 7, 8 out of 30 are less than that. So this is about the 27th percentile. Okay, I rounded. And how many wins did the team in the 46th percentile have? Okay, so we could do this a different way. We could say there's a certain number of teams out of 30 that ended us in the 46th percentile. So we multiply both sides by 30 to find out how many teams less than. So remember we rounded, so it's 13.8, which means that there's 13 teams less. Again, we're talking about teams less than. So let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So that means 83 wins. And then for the 16th percentile, we do the same thing. So 4.8, so 4 wins. So 1, 2, 3, 4. Looks like it's going to be 65. Okay, moving on. So percentiles are not that hard. We're not going to do too much with them. You just need to kind of understand what they're all about. We'll kind of hit those again later. But now we're going to talk cumulative relative frequency graphs. Okay, so the frequency table below describes the ages of the first 44 US presidents when they were inaugurated. So let's expand this table to include the relative percentage and cumulative frequencies. So this is what we're used to seeing. This is what we use for our histogram. Relative is going to put this in a decimal. So this is 2 out of the 44. 0.045. This is 7 out of those 44 presidents. 0.16. This is 13. Which is about 0.30. This is 12 out of 44. Which is 0.27. 7 out of 44 is 0.16. We had that from above. And 3 out of 44, 0.07. Now I rounded these a little bit, so it may not add exactly up to 1, but it should be about right. Then we have the cumulative So cumulative means you accumulate different scores. So if we start with 2, then the next one would be 2 and that 7 more. So in total, we'd have 9. And then from 13, we'd have plus the 9 we already have, so we'd have 22. And then we'd have 34, and 7 more on top of that. It's 41. And then we'd have 44. Okay, and we know that we added right because we have 44 total. Okay, this is just how it adds up because we're adding a little more each time. We're accumulating. And then cumulative relative frequency is a combination of these two. So this is going to still be 2 out of 44, which is about 0.45. This one is now 9 out of 44, which is 0.20. This one's 22 out of 44. I could do that one in my head. That's 0.5, 50%. Then there's 34 out of 44. See, we're approaching 1, 0.77. 41 out of 44, 0.93. And 44 out of 44, which is 1. See how we have the relative frequencies, but they're adding up. We could have also just added these all together, and that would have given us the same thing. Okay, so to make a cumulative relative frequency graph, we plot a point corresponding to the cumulative relative frequency in each class at the smallest value in the next class. Okay, so we did all this stuff. So the age at inauguration, so 44, then we added a little bit. So we could see here where it's steeper, this is where we had the most people. They were inaugurated at age 50 to 55. If we go back to our table, between 50 and 55, this 13 is the largest, closely followed by this one. Okay, this slope is telling us how much is being added. You see how this slope is very small and this slope is very small. There are less people being inaugurated at these times. So what is the age median? Well, median is right in the middle of the data, so at half. So at 50%, it's about 55. Why is this section between 50 and 55 the steepest? Because it had the most people added. If we want to estimate the IQR, well, this is, remember IQR is Q3 minus Q1. Well, Q3 is at about 75% and Q1 is at about 25%. So we're going to estimate it. So at about 75. So we could say roughly 58. And then the first quartile is at about 25. Which is about at 51. So the IQR is about 7. So the middle 50% of the data, the ages, is 7 wide. So that's pretty interesting. Again, it says estimate, so don't worry too much about being perfect. I would draw the lines to show that you know what you're doing. So even if your estimate's a little far off because you drew your lines terribly, we know you know what you're doing. I've seen AP tests graded that way, where they ask you to draw the lines, and if you draw your lines correctly and your numbers are a little off, you're still fine. Now we're going to talk about z-scores. We're going to use z-scores basically the whole year, but maybe we're going to do them a little different. But the main idea is we're standardizing the value. Z-scores can be compared to anything. So if we want to compare, if you're 2 pounds heavier than someone, that's not very much. But if you're 2 inches taller than someone, that's a little bit more. So your z-score would be higher. That's how we use this as a comparison. Oh, if x is an observation from a distribution that has a known mean and standard deviation, remember mean we can abbreviate as x bar and standard deviation as s of x from a sample. Remember if it comes from a population as mu and sigma. The standardized value of x is z. Okay, so what we're going to do is we're going to subtract the mean and divide it by the standard deviation, and we call that a z-score. So here is the height of students in the statistics class. So you can see we have 60 inches and we have up to 75. And then here's our one variable stats. So find and interpret the z-score for Lynn, whose height is 65 inches. Okay, so 65 is our value minus the mean. The mean is right here, 67, divided by the standard deviation, which is right here, 4.29. And we use our calculator to get that decimal. So it's negative 0.4662. So what this means is it's below our mean of 67 because it's negative. And what this means is it's the number of standard deviations above or below the mean. So this is about a half of a standard deviation below the mean. It's going to make a little more sense in a little bit, but that's how we're going to interpret it. So her height So Lynn's height is 0.4662 standard deviations below the mean. Brent is 74 inches tall. Find and interpret his z-score. So we're going to find it the same way. You know it's going to be positive because it's way higher than the mean. So we're still subtracting the same mean and dividing by the same standard deviation. Nothing has changed. There's a little tip on your calculator. If you go up and highlight and click enter, you can copy and paste and change. So 1.63. So I'm just going to interpret this. It's 1.63 standard deviations above the mean this time, which makes sense because he's way out there. So Brett is on the basketball team. The mean height of the basketball team is 76 inches. Brett's z-score is negative 0.85. Why is Brett's z-score negative? Well, Brent, compared to the rest of his classmates, is much taller than the rest of his classmates. But the basketball team's mean is 76. His height is below the mean of the team. So what is the standard deviation of the team members' heights? Well, we know Brett's height, and we know the mean, and we know his z-score. So we're just going to write an equation. Negative 0.85 equals his height minus the mean, which was 76, divided by the standard deviation of the heights of everyone on the team. Here's where you're going to start to love me. I don't care that you could solve this. If you hit menu and you go to algebra, solve, your calculator will solve this whole equation for you. So you need to type in comma x because it means it's going to solve for x for you. There you go, 2.35. So this means that the standard deviation is 2.35. You may absolutely do this on the AP test. I would highly recommend it. The only thing you need to do is you need to write this equation and then you can use the answer. You could say somewhere that you use your calculator to solve it if you want, if that makes you feel better, but you really don't. They're really just looking for this properly set up equation and the correct answer. And if it asks you to interpret, then you interpret. When we add and subtract by a, which is a constant, to every single data point, the measures of the center and location, so like mean, median, quartiles, percentiles, all those things, will add by a. The shape and the spread of the distribution will not change. Okay, if you think about it, if you have a distribution and every little part of that distribution moves up to here, well, the location and the center moved, but the spread and the shape did not move. I didn't draw a great picture, but you get the idea. When we multiply or divide every data by b, which is also a constant, the measures of center and location will multiply by b as well. The spread of the distribution will also multiply by b, okay, because it's going to get wider or narrower if the number is small. And the shape of the distribution will also stay the same. It might get wider, but the overall shape that we're talking about, the symmetric and the skewness and all that, will stay the same. So in 2010, taxi cabs in New York City charged an initial fee of $2.50 plus $2 per mile. In equation form, this could be modeled with the fare equals $2.50 plus 2 times the number of miles. At the end of a month, a businessman collects all his taxi cab receipts and calculates some numerical summaries. The mean fare he paid was 15.45 with a standard deviation of 10.2. So I'm going to call this x bar because it's a mean, and s of x because it's a standard deviation. It's not the population, it's from a sample. This is the mean fare he paid, but we're looking for the mean and the standard deviation of the lengths of his cab rides in miles. So this is the fare, and that equals 250 plus 2 times the number of miles. Well, all we got to do is solve that for miles, so we could use our calculator again and solve that. So 6.475 miles, that's the average number of miles, or the mean number of miles, okay, because we were talking about means, those measures of center. So remember, the measures of center always add and multiply, depending on what happens. But it's also asking us for the standard deviation. That's not a measure of center, that's a measure of spread. So if we add that 250, that's not going to do anything. So for our standard deviation, our equation is almost the same. However, we have our 1020 for the standard deviation, and this 250 is not going to do anything, so I'm not going to include it. But this multiplier of 2 times the number of miles will affect the standard deviation. Now we're going to do more examples of this in class, but basically you just need to remember that measures of center and location are affected by both adding, subtracting, and multiplying and dividing. But measures of spread are only affected by multiplying and dividing. So we could solve this pretty easily, so we don't need to use the solve feature. This is just 5/10 per mile. So this is standard deviation. Okay, so we're going to do a lot more of that in class and explore that a little, but there's the notes part. All right, density curves. So again, lots of different topics in this section. So far we get a set of quantitative data. We will make a plot of the data. We will look for the overall patterns, so shape, center, spread, and outliers. Remember, SOX. Shape, outliers, and unusual characteristics, center, and spread. So how we always describe it. We'll calculate a numerical summary to describe its center and spread. So this is where we do the one variable stats. Now we're going to add something. When you have a large number of data points, the pattern can possibly be described by a curve. This is what we're going to do a lot. So the histogram below is the number of days some guinea pigs survived after being exposed to some bacteria. So we could draw a curve to approximate the pattern we see in the graph. And we get that density curve so that we could kind of estimate it if there was more and more and more data points. The more points of data we have, the closer it would fit to that curve, and it will also help us see a lot of different things. Things to know about density curves. It is always on or above the horizontal axis, right? We can't have negative things. And it has exactly 1 underneath, right? Because remember at the beginning we talked about relative frequency. A density curve describes the overall pattern of a distribution. The area under the curve and above any interval of values on the horizontal axis is the proportion of all observations that fall in the interval. So here's some density curves. So the areas under density curves represent the proportion of data points. The median of a density curve has half of the data points on each side, so half the area. Okay, so this one's kind of nice because we have half the area on the left, half the one on the right. That one makes sense. So on this one, it's a little funkier because we have the median down here. Half of the area is over here. Half of the area is over here on the right. Again, we're talking about area. The mean is the balancing point. So on this one, because it's symmetric, the median and the mean are in the same location. It balances right in the middle, and half the area is split. But on this one, the long right tail, this skew, pulls the mean, right? Because if you were to balance this on your finger, those high values would move that balance point over, but the median would kind of stay in the same place. Why is this a legitimate density curve? Well, all the values are above the horizontal axis or on it, and the area is 1, and it says that. The proportion of observations lie between 7 and 8, well, that's 0.12. If we want to write it as a ratio, we could say 12 out of 100 if we wanted, but really 0.12 is perfectly fine. And we draw the approximate median. Well, the mean's going to be pulled a little by this skewness, and the median is going to split it in half. So we're just going to draw those. The median would be approximately there, and remember the mean's going to get pulled a little this way by that skewness. Again, we're approximating.